So in today's class or in this particular video, we are going to solve some of the gate problems, especially in the aerodynamics portion from gate 2007 aerospace part. So there are around 10 to 12 questions, and we will look into how to solve them and understand the basis on which we are solving it. So first question is a simple one, the drag divergence Mach number of an airfoil. As all of you know, drag divergence Mach number is the Mach number at which your drag will start to rapidly increase over your airfoil. So it's some subsonic Mach number or some Mach number, let's say, of the free stream, because let's say once you allow free stream to flow at that Mach number over your airfoil, your flow will accelerate on the top of your airfoil, and in some regions where the flow is supersonic and the curvature is so steep that the turn in the flow direction is really huge, and you see very, very strong shocks being formed there, and it will produce a lot of pressure drag for that matter. Or may not be pressure drag, it's right to call it as the wave drag. So that is nothing but the drag divergence Mach number. So drag is a fixed number for a given airfoil? Absolutely not. Based upon what the Reynolds number is and what the angle of attack is, it can definitely vary and cannot be given a single number. Is always higher than the critical Mach number. That is true. Critical Mach number is some subsonic Mach number, as you all know, at which you first start seeing sonic flow over your airfoil. So the reason why your drag divergence Mach number is always higher than critical Mach number is because critical Mach number critical Mach number is the Mach number at which you start seeing strong shocks on your airfoil. And to see strong shocks on your airfoil, your Mach number, free stream Mach number, will be sufficiently high, right? And your critical Mach number is when you first start seeing supersonic or sonic flow on your airfoil. So strong shocks come after your sonic velocities, the first onset of sonic velocity on your airfoil. So that is why you would need to definitely increase your Mach number to a value higher than your critical Mach number to see strong shocks being formed. Else, may not be that strong, and then your drag may not increase that rapidly. Is equal to critical Mach number? Absolutely not. Your drag divergence Mach number is usually higher than your critical Mach number because we define it as a time or the free stream Mach number for which you see strong shocks, right, and giving huge drag. This is definitely higher than the critical Mach number. Is the Mach number at which shockwave first appears? Absolutely not. There could be other Mach numbers where the shockwave first appears, but these shocks may not be of such strength to give a huge increase in the drag. So it may not be the first onset of shockwaves. Okay, so the right option is option B. Joukowsky airfoil is studied in aerodynamics because it is used in many aircraft. Absolutely not. We typically don't see Joukowsky airfoils being used that frequently. It's easily transformed into a circle mathematically. This is the right option that, So Joukowsky airfoils are nothing but when you take a circle in the XY coordinate and then you do a complex transform, or what they call as conformal mapping, you get a conformal mapping based upon some complex function where z is equal to x plus iy, and that is when you get a Joukowsky airfoil. And you can easily convert a Joukowsky airfoil back to your circle, or a circle back to Joukowsky airfoil based upon your conformal mapping function, and it's very straightforward to do. And the reason why it is of importance is because once you know the flow field over a circle, which is easy to calculate, right? Let's say you can, from potential flow theory, you can find the flow field around a right circular cylinder. That is basically nothing but the flow over a circle, right? So once you know the flow field around a circle, that is the velocity and everything at every point, you can easily map this velocity field or your flow field to the flow over an airfoil. So from flow over right circular cylinder, mathematically you're finding the flow over an airfoil. So that is the advantage of that. Simple, that has simple geometry, no, might be complex in cases. It has highest lift curve slope, absolutely not. One thin airfoil theory would predict a lift curve slope of 2 pi, and Joukowsky airfoils does not say anything in particular about that. So the right answer here is it easily transformed into a circle mathematically. One criteria for high-speed airplanes is that critical Mach number should be as high as possible. So in high-speed airplanes, you want your shock waves to be formed. High-speed airplane doesn't mean that you need to find supersonic regimes. It could be low subsonic, it could be high subsonic regimes like 0.8, 0.9, etc. And in such cases, you would want your critical Mach number to be as high as possible. So you would want a critical Mach number of maybe, let's say, 0.95, which basically ensures that, as long as I don't go near 0.95, my entire flow field over my airfoil is going to be subsonic, and I do not have to worry about shock. So for high-speed subsonic planes are usually designed with thick airfoils, thin airfoils, laminar flow airfoils, diamond airfoils. So usually we would design them with thin airfoils because if you compare a thick and a thin airfoil, so let's say there's a thick airfoil, and there's a thinner airfoil, and let's say both these airfoils are very similar in terms of the chord length, etc. So you can see that in the thicker regions, in the thicker airfoils, the flow will be, there's a huge curvature, and the flow will have to overcome this curvature or move along this curvature, and hence the acceleration of the flow will be higher. And there is higher chance that the flow will accelerate to Mach number greater than 1. But let's say, and assuming that the free stream that you're giving in for both these airfoils are the same. But for the same free stream velocity, if you take a thin airfoil, the curvature may not be that steep. So the flow acceleration also going to be correspondingly lower. So there's a much lesser chance that your flow will become supersonic on the surface of your airfoil that easily. That's why we would prefer thin airfoil. Laminar airfoil, it need not be, because usually the flow at such high speeds are turbulent. So we wouldn't go for this. Thick airfoils, absolutely not. And diamond airfoils, absolutely not. So diamond airfoils are basically can induce certain shocks. And it's a very discontinuous geometry. So the right answer here is thin airfoils. So here is an interesting problem where you have two pipes of constant sections but different diameters carry water at the same volumetric flow rate. So you have two pipes, pipe A, pipe B, and they have constant section, meaning that at every location, every actual location, your cross section is constant. So one has a diameter D, and other one has a diameter, let's say D prime for that matter. And they want us, and they carry the same volumetric flow rate. So volumetric flow rate, let me represent by V dot. All right. And the Reynolds number based upon the pipe diameter is. So they want us to find how the Reynolds number based upon the pipe diameter looks like for both these guys. So let's try and do that. So Reynolds number for pipe with diameter D, which I called as RED, is nothing but density of the fluid, velocity of the fluid in pipe diameter D, diameter of the pipe, and viscosity. And so density and viscosity is going to be constant for both the pipes, right? Because the same fluid water that is flowing. So rho V, Vd prime is the velocity of the fluid in pipe with diameter D prime, and D prime is their diameter, let's say. And then I'm going to take the ratio between both, let's say Red by Re, D prime. And I'm going to get, rho, I can cancel out, mu, I can cancel out. I'll end up it as nothing. Vdd and Vd prime, D prime. So here we know that D and D prime they are different, but we do not have much information on Vd and Vd prime. So let's use the volumetric flow rate guy here. So volumetric flow rate in pipe D is nothing but area of pipe, area of the pipe with diameter D times velocity of the pipe with diameter D. And the same volumetric flow rate is going through the pipe with the diameter D prime as well, right? So that is nothing but area of the pipe with diameter D prime and velocity, velocity of the pipe with diameter D prime. So area of pipe with diameter D, so I can equate both these guys, right? Because their LHS is the same. So area of pipe with diameter D is nothing but pi D square by 4. And Vd is the velocity of the pipe with the same diameter. Area of the pipe with diameter D prime is pi D prime by 4, pi D prime square by 4 times Vd prime. Again, slot pi 4, 4. So I can essentially write Vd by Vd prime is nothing but D prime square by D square. Just rearranging the terms right here. Now this VD by VD prime, I'm going to substitute in my Reynolds number equation. All right, this equation. So when I substitute RED by RED prime is nothing but VD by D prime, VD by VD prime, that is D prime square by D square into D by D prime. So D by D prime came from the older ratio that we looked into, that is this guy. And VD by VD prime was replaced as this. So I can cancel out this guy, D prime I can cancel out. So Reynolds number of pipe with diameter D divided by Reynolds number of pipe with diameter D prime is equal to D prime by D. All right, let's keep this result in mind, and then let's try to use the same result in our result discussion. So here we can see that so let's say I'm going to compare the I'm going to compare just let me write it. So yeah, so Reynolds number of pipe with diameter D divided by Reynolds number of pipe with diameter D prime is nothing but which we saw as D prime by D. Now they're asking us Reynolds number based on the pipe diameter, same for both pipes. So from the equation, you can see that only if D prime is equal to D, we can say that the Reynolds number is also the same. But they have told us that they have different diameters. So this cannot be true. Is larger and narrower pipe. So let's say you assume that D prime is going to be higher than D. So D pipe with diameter D is a narrower one. So from this expression, we can see that your RHS is going to be greater than 1, right? Because D prime is greater than D. So your LHS also should be greater than 1. So that implies your Reynolds number of diameter D is greater than the Reynolds number of diameter D prime. So which basically tells you, so D is the pipe with narrower diameter. So your Reynolds number is definitely higher than that. Or let's take a different case where D prime is less than D, where D prime is the narrower one. And so in this case, your RHS is going to be less than 1. So your LHS is also going to be less than 1. So that basically implies RED is lower than RED prime. Again, telling you that Reynolds number is higher in the narrower pipe. So option B is the right one. And it's smaller in the narrower pipe, which we saw that it's not true. It's higher in the narrower pipe. And depends upon the material of the pipe. Absolutely not, because there's nothing which suggests in the entire expressions that we wrote that there's any sort of dependence on the pipe diameter. Okay. Now let's look at this case where you have two airfoils of the same family are operating the same angle of attack. So let's say I have two airfoils, let's say NACA 0012, and they're operating at the same angle of attack, let's say 2 degrees, or airfoil A and airfoil B. And the dimensions of one airfoil are twice as large as the other one. Let's say airfoil A has a chord of C, while airfoil B has a chord 2C. But they're operating at the same alpha, 2 degrees, and they are the same family, 0012. The ratio of the minimum pressure coefficient of the larger airfoil to the minimum pressure coefficient of the smaller airfoil. So we know that pressure coefficient is nothing but Cp is defined at every point on the surface of the airfoil, that is pressure at that point minus P infinity, that is pressure of the free stream, divided by half rho V infinity square. All right. So at every single point, you can, based upon what is the pressure at that point, you can define what is your CP. And on the entire surface of your airfoil, there will be one point where your CP will be the least. So now there will be one point here where your CP will be the least, and there's another point over here where in this airfoil your CP will be the least. And they're asking us what is the ratio between both. So to understand this, let's take a simpler problem where you're dealing with right circular cylinder. One circular cylinder with size D, other with size 2D. D, and this is a size 2D. So we know that Cp here is given by, for right circular cylinder from potential flow theory, it's given by V sine square, 1 minus 4 sine square theta. And the least value of Cp is when sine theta is equal to 1, where theta equal to 90, right? So these locations, theta equal to plus minus 90. So that will basically give me 1 minus 4, and that is minus 3. Minus 3. So Cp, least value of Cp is minus 3. And you can see that in both these cases, the least value of Cp does not depend upon the size. In both the cases, so if I draw these two guys on top of each other, concentric. So for one guy, it is at a location of, radius r and theta equal to pi by 2. And for this guy, it is at a location radius 2r and theta equal to pi by 2 in r theta coordinate system. So irrespective of the location, so here, one is at location r, other is location 2r, but their value was the same. So Cp minimum here divided by Cp minimum here is nothing but minus 3 by minus 3, that is 1. So the same logic can be applied to your airfoil as well. So irrespective of the size of the airfoil, the least value of Cp developed will be the same. And the only thing is that the location might be a bit different in each case. So though your pressure which is developed will be different. So pressure, the least value of pressure will be different between this and this, but your Cp, which you are non-dimensionalizing, will be the same. Because that is the beauty of these non-dimensional numbers, where as long as you keep your other non-dimensional numbers like Reynolds number, Mach number the same, and angle of attack as well. So your all these non-dimensional numbers will be equal, and the actual values might be different. Let's say like P and lift and everything will be different, but their non-dimensional values will be the same. So even in these two cases, though the locations where the Cp minimum is occurring will be different, but their values will be one and the same. So the ratio will exactly be equal to 1, which is option C. In this question, wing A has constant chord C and span B. So you have wing A, it has a constant chord C and span B. And there is wing B is identical, meaning that let's say if this is a airfoil 0012, this is also 0012. And this has chord C but span 4B. When both wings are operating at the same geometric angle of attack, and so both are operating at the same angle of attack alpha. At angle of attack at the same subsonic speed, then what they're asking us is, will wing A and B produce the same lift coefficient? We know that this is not possible because wing A is longer than wing B. So a longer wing will have, let's say, aspect ratio of wing A is nothing but B by C. And aspect ratio of wing B will be 4B by C. Which means that, the 3D effects or the lifting line effects will be lower for wing B and than wing A. So which basically tells you that, so let's say if I'm looking at the lift curve slope, so lift curve slope, we know that for a wing is given by A equal to A naught divided by 1 plus A naught by pi A ARE. So A naught is the lift curve slope of the airfoil used, and we know that both use the same airfoil. And AR is the aspect ratio, E is the efficiency factor. Let's say we take it 1 in this case. And so as you can see from this expression that the higher my aspect ratio, my A will be closer and closer towards A naught. That is the wing lift curve slope will be closer to the airfoil lift curve slope. So my wing with size 4B will have higher A than, okay, that is wing B than lift curve slope of wing A. So that basically is nothing but lift curve slope of wing B will be greater than lift curve slope of wing A. So CL, which is given by lift curve slope times alpha, and both of them are running at the same alpha, right? So that implies CL of wing B will be greater than CL of wing A, given that, it's the same Reynolds number and Mach number over the two wings. So this is not really possible. Wing A produces smaller lift coefficient than wing B. That is true, but there we need to look at the free stream conditions as well. So we can never really concretely say this. And even this, we can never really say for concrete, because I mean this is not really possible, right? Because even if the Mach numbers, and again, if you're using a different Mach number, Reynolds number, this equation would shift in one particular direction or the other. And the right option here is option D. The free stream Mach number decides which wing will produce higher lift coefficient. So which is very true, because when in a compressible scenario, your lift coefficient will need to have a correction factor that is 1 minus m infinity square. So based upon what is the Mach number in each case, let's say for wing B and wing A, this compressibility factor correction will be different, and your CL will be different accordingly. So that will also should be taken into consideration while saying which one produces higher CL value or lift coefficient. So this option D is the right answer here. So in this question, a numeric problem, they're telling us that there's an airplane flying at 10 kilometer altitude. Outside air temperature and density is 223 Kelvin and 0.413. So at 10 kilometer altitude, your density of air is 0.413 kg per meter cube, and your temperature is nothing but, let me call it rho infinity and T infinity, something but the free stream conditions. And this is 223 Kelvin. The airspeed indicator of the airplane indicates a speed of 60 meters. The indicated airspeed, that is VIAS, or the equivalent airspeed, whatever is being calculated by the indicator on the aircraft, gives you a speed of 60 meters per second. And the density of air at sea level is 1.225, right? And the gas constant is 228. The stagnation pressure measured by the pitot tube mounted on the wing tip is. So they are asking us what is the stagnation pressure. So our first instinct would be to use Bernoulli's equation. P naught is equal to P infinity plus half rho V infinity square, rho infinity V infinity square. But we need to do some pre-work before using this, because this is an expression can be only used in incompressible scenarios. So we need to be very careful and make sure that this scenario is definitely incompressible. To find if it is compressible or incompressible, we need to find the Mach number. And Mach number is nothing but the velocity, which is nothing but the true airspeed divided by root gamma RT. In the question, they've given us the indicated airspeed, and we need to convert that to a true airspeed. So true airspeed and indicated airspeed are given by the ratio of rho naught by rho, where rho naught is the density at the sea level and rho is the density at whatever the altitude. So which we already know. So the true airspeed in this case will be nothing but we indicated airspeed is 60 into root of 1.225 divided by 0.413. And in this case, it gives you true airspeed is around 103 meters per second. All right. And now let's calculate what is the Mach number. Mach number will be 103 divided by root of gamma RT. We can take gamma to be 1.4 in this case, 288 Kelvin. 288 is the R, and temperature is 223. And your Mach number will be around 0.34, which is definitely Mach number 0.34 is greater than 0.3, which we call as the rough compressibility effects domain, so or the limit. So if my Mach number is greater than 0.3, I cannot use my Bernoulli's equation. I need to use gas dynamics relationships. So I cannot use the Bernoulli's equation over here. I need to use the gas dynamics relationship where P naught by P or P infinity is given by 1 plus gamma minus 1 by 2 m square whole power gamma by gamma minus 1. So the P naught is the stagnation pressure and P infinity is the static pressure. So P naught by P is equal to nothing but 1 plus gamma minus 1 by 2. It's nothing but 0.2. 1.4 minus 1 by 0.2. Mach number is 0.34. Square of it and whole power 1.4 by 0.4. And P is something which we can calculate from gas, ideal gas law. P equal to rho RT. Rho at that altitude is 0.413. R is 288 Kelvin. R is 288 joule per kg Kelvin, and T is 223. So your P is around 2.6 10 power 4 Pascal. 10 power 4 Pascal. And then if you substitute this P in this expression, your P naught would turn out to be around 2.8 10 power 4 Pascal, which is in the given question, option C. So this is how you do it. So make sure that you understand which compressibility regime does it come under, and then use your relationships appropriately. Else you might run into trouble. In the next question, they're asking us, a turbulent boundary layer remains attached over longer distance on the upper surface of oil than laminar boundary layer. So they're asking us why a turbulent boundary layer, let's say turbulent boundary layer, will remain attached more on top of an airfoil surface than a laminar boundary layer, which might separate earlier. So the main reason is option A, that is the turbulent boundary layer is more energetic and has overcome the adverse pressure gradient. So in turbulent boundary layer, there's a chaotic motion of fluid here and there. So even if flow is moving at an adverse pressure gradient and losing energy, the random motion of the flow can give, impart energy to the flow whose energy is being taken out, and then the flow will be able to continue much longer. But in a laminar case, it is not possible that the fluid which is being impeded does not get re-energized in energy, and then the flow will easily separate. And let's look at the wrong options as well. The laminar boundary layer develops more skin friction. Not really. It's a turbulent boundary layer will develop more skin friction because in turbulence you have these eddy structures over which your flow has to go. So this act like an apparent skin friction effect. The turbulence causes effective coefficient of viscosity to reduce. Actually, turbulence causes the effective viscosity to increase. For that matter, and turbulent boundary layer is thicker. So usually the turbulent boundary layer is thinner than the laminar boundary layer because a lot of the a huge part of the boundary layer will be re-energized because of the random motion, and only will be very small region where you can see a proper velocity gradient. So it's a much thinner boundary layer for turbulence. So option A is the right answer. This is another number problem. The laminar boundary layer over a large flat plate held parallel to the free stream is 5 mm thick at 0.2 meters downstream from the leading edge. So what they're saying is that you have a free stream which is kept parallel, which have a flat plate which is kept parallel to the free stream and is developing a boundary layer profile. And at a distance of 0.2 meters from the leading edge, your boundary layer thickness is 5 mm. And they're asking us at a distance of 0.8 meters from the leading edge, what is the thickness? Let me call it delta. It's a very simple problem. You just need to keep in mind what is the Bloch's solution for laminar boundary layer thickness, which is given by phi x root Rex, where Rex is nothing but the Reynolds number based upon your physical distance x, that is the distance from the leading edge. And rho and v are the density and velocity of the free stream. So let's look at the quantities that we have. Delta at 0.2 meters from the leading edge is given by 5 into 0.2 divided by root of rho infinity v infinity 0.2 divided by mu. And delta at a location of 0.8 is given by 5 into 0.8 divided by root of rho infinity v infinity 0.8 divided by mu. Let's take the ratio between both. So if I take the ratio between both, I can cancel out 5 rho infinity v infinity mu, rho infinity v infinity mu, and then I am left with, so if I were to write it down here, delta at 0.2 divided by delta at 0.8 is equal to 0.2 So I can cancel these two out, and this will give me root 0.2, and this will give me root 0.8. So root of 0.2 by root of 0.8. So that is nothing but 1 by 4, and root of 1 by 4, and root of 1 by 4 is 1.2, or 1 by 2. So which basically tells you that boundary layer thickness at location 0.2 by boundary layer thickness at location 0.8 is equal to half. So if I use that same relationship over here, so delta at 0.2 divided by delta at 0.8 is equal to half. So if my delta at 0.2 is 5 mm, my delta at 0.8 is nothing but 5 into 2. So 10 mm would be the boundary layer thickness at 0.8 meters. So what they're telling us is that for the control volume shown in the figure below, the velocities are measured both at the upstream and the downstream end. So they are giving us a control volume like this. All right, control volume like this. And inside the control volume, you have an airfoil. And at the inlet of the control volume, you have a uniform free stream. At every height, the velocity of the free stream is u infinity. But let's say at the end of the control volume at the outlet, you can see that the uniformity of the free stream is gone. That because of the flow over the airfoil, the flow has really lost its momentum on flying over the airfoil, or in fact flowing over the airfoil, and it forms a profile like this, like a linear velocity profile, 0 at the middle location, and then increases to u infinity at the edges, and the velocity profile is given by so and so. Now, what they're asking us is that the flow of density rho is incompressible. It's incompressible flow. It's two-dimensional and steady. The pressure is P infinity over the entire control surface volume. That over the entire surface of the control volume, my pressure is P infinity. And they are asking us the drag on the airfoil. What is the drag force on your airfoil? And they've given these options. So, so here you would need to, your drag force, you're here to find out force, right? So forces are, the force, the only law in which we use forces is nothing but the Newton's second law, or the momentum conservation law. Momentum conservation law. So, so you would definitely need to use your momentum conservation law for this. But before that, you have a very small problem to address. That is, at the outlet, you have a height of h and h. So you have a height of 2h, right? But the inlet, you don't know what this height is. Let me call it as h prime for the time being. So you would need to find what is the area of the inlet and the outlet, right? So let's say it's a two-dimensional flow. I'm assuming it to be infinitely extended. I mean, dimension in the other direction or into the plane of the paper is unity. So I can assume that for this case, since considering it like a two-dimensional or like a airfoil kind of scenario. All right. So first I need to find this h prime guy. So to find h prime guy, we always have our mass continuity equation. So let me try and use that. So at the inlet, mass flow at the inlet is nothing but a velocity u infinity, which is constant throughout, right? The velocity u infinity is constant throughout, times the area, or let's say we call it as rho, density of the free stream velocity, and then the area. Area would be nothing but h prime times unity. And what is the mass flow at the outlet? Mass flow at the outlet, it's not that straightforward, because you know that the velocity is not constant throughout. So you would definitely need to integrate. So we know that our density is rho, and your velocity, your flow rate over the area needs to be integrated by u times dy from 0 to h, and since you have so that is from 0 to h, And the same amount of flow rate is going from 0 to minus h as well. So it becomes 2 times of this, 2 times of this, and then times the dimension and the plane perpendicular to the paper, that is 1. So 2 rho into integral 0 to h, and u is nothing but u infinity h by y, u infinity h by infinity h into y, infinity y into h into dy. And I can take u infinity and h outside because they are constants. And in the integral, I would be left with 0 to h y dy. And this will be nothing but m dot outlet is nothing but 2 rho u infinity by h into y square by 2 integral 0 to h. So when I evaluate this integral, I'll be getting 2 rho, this 2 and this 2 can be cancelled out. So let me erase this guy. And so it'll be rho u infinity h into h square. So this will be nothing but rho h and h you can cancel out, and rho u infinity h is the mass flow rate at the outlet. All right. So mass flow rate at the inlet, that is nothing but rho u infinity h prime is equal to rho u infinity h, that is the mass flow rate at the outlet. So rho infinity cancel, and that basically tells you h prime is equal to h. Or so at the inlet, the height of the domain is just h, while at the outlet it has become 2h. So which you can easily understand that that your velocity is being reduced, right? So you're losing a lot of velocity. So to maintain the mass flow rate, you would need to increase the area over which the flow is moving. All right. So that basically gives you what is h prime. Now let's apply our momentum conservation. So momentum conservation basically tells you the rate of change of momentum, m dot out minus m dot in is nothing but the net force that is acting, right? So the loss in momentum over here. So I'm sorry, maybe it may not be good to use the same notation. Let me use capital M. That is momentum that is come in minus momentum that has gone out will be basically nothing but the force that has been acting inside your domain, right? So it comes, a flow will come with a higher momentum and leave with a lower momentum, and that momentum is being consumed by the drag force exerted by your airfoil, right? So that is so this basically, this analysis can give you what is the net drag force that is acting over your airfoil. So momentum of the flow coming in minus momentum of the flow going out is will be nothing but the net drag force acting on your airfoil. This is the momentum conservation law. All right. So momentum that is coming in, so that is nothing but the mass flow rate that is coming in times your velocity with which the flow is coming in. And momentum going out is nothing but the mass flow rate going out times the velocity with which the flow is going out. I'm just varying with the space, so we would need to integrate accordingly. So let me look at mass flow rate that is going out separately. Mass flow rate that is going out would need to be integrated as integral 0 to h. So rho is a density, and use the velocity of the flow that is going out, and you would have your velocity that is to the mass flow rate times velocity gives you a momentum flow rate, so that becomes a rho u square, and then integration over your area dy times unity. Unity to consider the dimension of the perpendicular direction. So rho u square dy would give you integral of that from 0 to h would give you your momentum that is moving out. So let me calculate that. Momentum that is going out is equal to, I can take rho outside, and you have integral u square dy 0 to h. And then I again, 2 times of this, so as to account for the top and bottom half of the domain. So that is this particular portion, and then this particular portion. So 2 times of this, rho u square is nothing but u infinity square by h square into y square into dy. So let me take u infinity square by h square outside. So rho u 2 rho u infinity square by h square, and then what I'm left with is y square dy integrated from 0 to h. And so that is nothing but 2 rho y cube by 3 from 0 to h. So that would be nothing but 2 rho u infinity square by h square into h cube by 3. So I can cancel this guy out. So what I get is 2 rho u infinity square h by 3. So going back to our case, so I got what is the net momentum that is going out, and the momentum that is coming in, and I need to take the difference between both. So let me do that. So momentum that is coming in is given by rho u infinity square h, and momentum that is going out, which we found it as 2 rho u infinity square h by 3. 2 rho u infinity square h by 3. And this resultant is the net force that is acting. So when I take, convert these fractions, so I'm going to end up with 1 by 3 rho u infinity square h is equal to net force. And this net force is nothing but the drag force that is acting, F drag. Because any loss in the momentum, that will automatically be accounted for towards the drag force, right? So in this question, the correct answer is option D, rho u infinity square h by 3. So keep in mind, guys, whenever you have a velocity profile, you would need to integrate to find your mass flow rate, and then the momentum flow rate, or rate of change of momentum. So once you do that integration and then you take the differences accordingly, you will definitely get your answers right. All right. So here, this is an interesting question. An airfoil section is known to generate lift when placed in a uniform stream of speed u infinity and at incident alpha. So let's say that you have an airfoil, you put it at a free stream at an incidence alpha, and then velocity v infinity, it'll generate lift, right? A biplane consisting of 2 such sections of identical chords separated by distance as shown in the figure. So there's a biplane configuration where you have airfoil B and airfoil A. They are kept at a vertical distance of h from each other, and both are identical. Both are exactly the same airfoils with the same size, same family. With regard to this biplane, which of the following statement is true? Both airfoils experience an upwash and increase in approach velocity. Both airfoils experience a downwash and decrease in approach velocity. Both airfoils experience an upwash and airfoil experience. So what they're asking us is that just because of this configuration, will A and B will increase the net increase in the flow speed? So let's say free stream is coming at V infinity, but because of the interaction between these two airfoils, will V infinity become higher? And the other question is, would they receive an upwash or a downwash? So let's try to find it out. You need to just think very logically over here. So you have airfoil A and you have your airfoil B. This is B, this is A. They're separated by a height h. So now we know that in a normal airfoil which is in free stream, it has got so much area. It's not a constraint kind of scenario, right? You have you have sufficient area on the top and the bottom without causing any acceleration. But as you can see that as a free stream is coming towards your biplane, you can see that from an infinite kind of area, it has been forced to go through an area with dimension h. So which essentially means that as the flow enters in this region, your flow is definitely going to get accelerated. And or the top of or these two surfaces, it may not get accelerated because you have sufficient area in these two dimensions. But in this constricted area, you're essentially letting air from a huge area to move through an area of smaller dimension, which will essentially mean that your flow is going to be accelerated. So essentially telling you that at these locations, your flow is going to move at faster velocity than what it came by. So essentially meaning that your approach velocity is going to be higher. Approach velocity is higher for both airfoils because there's acceleration for airfoil B here and there's acceleration for airfoil A over here. So an increased approach velocity for both the airfoils. All right. And now to answer the question of upwash or downwash. So for this, you need to carefully look at how these airfoils are aligned. You can see that the bottom surface of the airfoil or the flat surface of the airfoil is like this, and then the curved surface of the airfoil is in this way, and that is the same for airfoil A as well. So this has a profound impact on how whether we are seeing an upwash or a downwash. So let me explain. So let's say I have kept the airfoils in this way, airfoil B and airfoil A. And mind you, they are at the same angle of attack. So let's say flow is moving in these locations, right? So in these locations, you can ignore these two locations. So in these locations, you can see that this is the top surface of the airfoil. So this is the location with negative pressure difference, and this is the region with positive pressure difference, right? So these are the regions where, so this curved surface is the region where your air will in fact accelerate and the pressure will be lower. And so in this airfoil, if you see, this is the location where you have a positive pressure, and this is the region where you have a negative pressure, right? Because the curved surface over here. So there's more flow acceleration over here, and there's a negative pressure formed over here, like negative pressure difference in these cases, in these regions, and positive pressure difference in these regions. So as you know that flow will always tend to go from a region of positive pressure to negative pressure, right? Or let's say from high pressure to low pressure, to be more accurate. So this region has lesser pressure than this region, and they are in the same domain, right? They are not separated by anything. So you could typically expect your flow to move towards the sky. So you see the flow streamlines moving towards the sky. So this basically, will create an upwash, and that is true even not only for airfoil B, for airfoil A as well, because any free stream that is coming in will be taken up in this way. We'll have, since it is subsonic flow field, the free stream, whatever the flow field over here will influence something over here as well, and your free streams are essentially bent. So when these free stream essentially bend, initially your free stream was coming in a straight, let's say, in the straight manner. Now you have some initial, some added on velocity, in the upward direction over here. So your resultant velocity will basically be in this way. So that essentially would increase your angle of attack, or you would get what we call as an upwash. So for both these airfoils, we'll essentially make sure that the free stream is coming at it, in a curved manner because of this pressure difference that is existing in this location and this location. So because of the curving, you can typically expect, if initially free stream was coming like this, it gets an added on velocity component in this way, and the resultant is in this way. So this is basically like an increase in the angle of attack. So that is why you would typically see so initially you can see that if this is the chord of your airfoil, so your angle of attack was between V infinity and the chord, which is small. Now because of this upward velocity component, your free stream got inclined like this, and you have a higher angle of attack now. So that is why it creates an upwash. Let's say that is why I asked all of you to take note of the shape of the airfoil and how they're oriented over here. Because if the curved surface was on top, for both these cases, then your answer would be that both will experience a downwash. So the right answer here is that both experience an upwash and then an increased approach velocity. Increased approach velocity because of the flow constriction, and then the upwash is because of the negative lower pressure in this region and higher pressure in this region, essentially curving the streamlines towards this, because flow tends to go from region of high pressure to low pressure. So option A is the answer. There's another simple problem. A circular cylinder is placed in a uniform free stream of ideal fluid which acts normal to the flow. This is like the flow over the cylinder, flow over right circular cylinder. And it is an ideal fluid, basically rotational incompressible potential flow. Relative to the forward stagnation point, the angular position along the circumference where the speed along the surface is equal to the free stream speed. So what they're asking us is that with respect to your forward stagnation point, so we know that this point is your most forward location of your stagnation point, right? With respect to this guy, you need to tell you need to give the answer towards where are the locations on your airfoil where your location at that particular point is equal to the free stream velocity. All right. So which are the locations where your free stream velocity is equal to V infinity, or free stream the velocity of the surface of your cylinder is equal to the free stream velocity. So we can easily do this. Let's say Cp for a right circular cylinder is given by 1 by V infinity square, right? So let's say for all the locations where my V equal to V infinity, that implies that my Cp should be 0, right? So V by V infinity, this becomes 1 minus 1 is 0. Now, how does that help us in getting these angular location? So for that, you need to look at the other definition of Cp for right circular cylinder, where I can define Cp as 1 minus 4 sine square theta. And we know that for locations where my V equal to V infinity, Cp is equal to 0. So that basically tells me that 1 minus 4 sine square theta is equal to 0. So 1 is equal to 4 sine square theta. And that implies that sine square theta is equal to 1 by 4. And sine theta is equal to plus minus 1 by 2. So wherever my theta is plus minus 1 by 2, I can say that, my V equal to V infinity. Now, for right circular cylinder, from conventions of mathematics, we measure the theta in this particular manner. We measure it with respect to the aft stagnation point. So theta would be taken positive counterclockwise starting from this location. So we know that, so this theta mathematically is determined in this way. But in the question they're asking us, we need to measure with respect to the forward stagnation point and not the backward stagnation point. So first, let's characterize the location with respect to the backward stagnation point by the typical mathematical convention, and then we can convert it later on. So with respect to the typical mathematical convention, theta is positive half at locations 30 degrees, pi by 6, and then theta 180 minus 30, that is 150 degrees. Then theta is minus half at location, these two locations where theta is nothing but pi plus 180, that is 210 degrees. And also theta is 360 minus 30, that is 330 degrees. So with respect to these locations, so these are the locations where my theta will be, sine theta will be plus minus half. Now, so these are 30 degrees, 150 degrees, 210 degrees, and 330 degrees. So let me maybe draw that up just to make things clear. All right. So let me mark these locations with my red ink: 30 degree, 150 degrees, 210 degrees, and 330 degrees. So let me mark the angles as well. 30, 150, and this is 210. And then you have your 330. All right. Now this is with respect to this stagnation point. Now let's try to do it with respect to the front stagnation point. So with respect to front stagnation point, 210 degrees is basically nothing but if I take 30 degrees from here, right? So 30 degrees with respect to front stagnation point is one stagnation location. And 330 degrees is nothing but 180 minus 330 minus 180. So that will be nothing but 150 degrees. So from my front stagnation point, if I go 150 degrees, I'm going to reach the 330-degree point. So from my front stagnation point, if I go 150 degrees, I'm going to reach the stagnation, these two, the stagnation point. If I go 30 degrees, I'm going to reach the stagnation point. Now to reach this guy, I need to go nothing but 180 plus 30. That is from here, if I take 180 degrees and then I go another 30 degrees, I reach the stagnation point. So that is 210 degrees. And if I, so from the front stagnation point, this entirety is 360 degrees. So to reach the stagnation point, I need to go till 360 minus 30, that is 330 degrees. So if I go from here and take a 330 degrees turn, I reach the stagnation point. So the angular locations where I get my V equal to V infinity is 30, 150, 210, 330. That was very similar to my old convention as well, but just to be on the safer side of the question, with respect to front stagnation point, it's at 30, 150, 210, and 330. All right. Now here is another simple question. The span-wise lift distribution for 3 wings is shown. So there are 3 wings R, Q, P, and their span-wise lift distribution is shown. That is nothing but CL. What is the lift? So if this is the half span, let's say if this is the half span of your wing, and at each location you have an airfoil, right? And each airfoil will generate a CL, get a given angle of attack. So what they're doing is that at each location, they're finding the CL of the airfoil divided by the CL of the entire wing in itself. And so we know that airfoil will generate more CL than the wing because of the 3D wing effects and things like that. So you can see that in certain locations is greater than 1. So in this question, they've given you for each of this wing, how does the CL vary? So in this wing P, the CL generated by the airfoil varies in this way. It starts at 0.8 and then increases to, let's say, 1.1 and then goes to 0 at the wingtips. And Q again, starts in a very similar way. It starts at 0.9 and then increases and then decreases. While R basically starts at the very high value, it does not show an increase decrease, but it just shows a continuous decrease with respect to your span-wise location. So in the above figure, CL refers to the sectional lift coefficient, which is nothing but at each section you have an airfoil. What is the lift coefficient of that airfoil? And this capital C refers to the lift coefficient of the wing. Y is the coordinate along the span, and this is the span of the wing. So Y is nothing but the coordinate representing the location along the span where these airfoils are present. A designer prefers to use a wing for which stall begins at the root. Which of the wings will he choose? So a designer wants to choose a wing where the stall will begin at the root. That is at at the location 0. 0 is the root of the wing, and 1 is the tip of the wing. So he's asking, out of RQP, which one should I choose so as to make sure that my stall begins at the root? And the answer here is that, and stall, as you guys would know, is a phenomenon that, let's say if you have an airfoil, if I keep increasing the angle of attack of my airfoil beyond a certain value, I do not get an increase in CL, but I get a drastic drop in my CL value, and this is what we call as a stall angle of attack. And beyond stall angle of attack, what happens is that the flow gets really separated from your airfoil, and then it creates a huge amount of pressure drag, and then it creates very less lift. So now they want to make sure that, in case if I reach some stalling, I want to make sure that my root will stall first than my tip. So if you look at all these 3, I can easily find that the highest value of CL is at location for wing R, which means that let's say as long as they are using the same airfoil at every section of my wing, that this section must be at a higher angle of attack than any other section, or or by some reason or the other, this section, the section which is very close to the root, is giving higher CL value than any other section. So which means that if I increase my angle of attack for the entire wing, I'm definitely going to get more CL at the root than in the other location. So which essentially means that this location is more closer to stalling than any other location because this is already at a higher CL value than any other locations that we have. So imagine if, let's say if I have the airfoil used in this case has a stall angle of, let's say, 8 degrees. All right, 8 degrees, and my lift curve slope is so and so. So at the root, I might be already operating at a, let's say, an angle of attack 7 degrees, and that's why my CL is really high. And then my as I go towards the tip of the wing, I'm going to keep it at lower and lower angle of attack. So maybe in this location, I'm keeping it at an angle of attack 4 degrees. At this location, I'm keeping it at an angle of attack 1 degrees, etc. And that is where you can see that the CL is continuously reducing. So which essentially means that if I increase the entire setup by an angle of attack of maybe 2 degrees, only in this location where my angle is already kept at 7 degrees close to stall angle, it becomes 9 degrees, and then this location would stall. While in the other locations, my angle of attack goes to, let's say, 6 degrees or 3 degrees, and this doesn't stall. So to make sure that I am stalling the root first, I need to choose a configuration where my CL is highest at the root, and which is nothing but the R configuration. So option C over here. Here is another simple problem. So in the question they've given a model wing of rectangular platform has a chord 0.2 meters and span 1.2 meters. So there is a wing which has a rectangular shape where it has a total span of 1.2 meters and a chord of 0.2 meters. It has symmetric airfoil section whose lift curve slope is 0.1 per degree. So the airfoil used in this all these sections are symmetric, and they have a lift curve slope A0, let me call it as 0.1 per degree. And if and it's always safer to convert them to radians, just to make sure that you are not going wrong in any of the calculation. So let me convert it to radian. So this will be nothing but around 5.72 per radian. All right. When the wing is mounted at 8 degrees angle of attack and a free stream of 20 meters per second. So the angle of attack of the wing is 8 degrees. And my free stream is acting at 20 meters per second. All right. And the wing is found to develop a lift of 35.3 newtons when density of air is 1.225. Now the lift curve slope of the wing is, now they've given the lift curve slope of the airfoil used in the wing, but we need to find the lift curve slope of the wing in itself, which is nothing but the A, which I'm calling it over here. And this is true, right? Because the wing lift and airfoil lift curve slope may not be the same because of 3D effects. So to find A, they've given us the lift, right? And first let us find CL from this lift. So CL for the entire wing is nothing but lift by half rho V infinity square, and the planform area of the wing, that is nothing but chord times the span. So lift here is 35.3 newtons, and half is half, rho is what they've given in the question is 1.225. Velocity V infinity is 20 meters square, and chord is 0.2 and span is 1.2. So that basically, we have everything that is required, and then that basically gives us a CL value of 0.6. So we found what is the CL value, immediately. Now to find the lift curve slope of it, so we know that CL is nothing but CL alpha times alpha, and it's a symmetric airfoil, so we do not have alpha L equal to 0. That is the lift zero lift angle of attack, 0 over here. CL is 0.6, and CL alpha is something we need to find, and alpha is 8 degrees. And CL alpha is nothing but 0.6 by 8, and that is nothing but 0.075 per degree, which is nothing but option C. Very simple. So we do not really have to use the lift curve slope of my airfoil till now. And we see that the lift curve slope of the airfoil is higher than the lift curve slope of the wing. Next, they're asking us the span efficiency factor of the wing. Span efficiency factor, that is nothing but the E guy. We can easily find them by using our relationship that connects A and A naught. The lift curve slope of your wing is equal to lift curve slope of your airfoil A naught plus 1 divided by A naught by pi AR. And then let me call this the span efficiency factor. Now here you need to keep in mind that this span efficiency is nothing but, like a truncation of all the Fourier coefficients for that matter. So all the truncation of the Fourier coefficients, if you do, that's how you get your efficiency factor over here. So let's not go into too much and then detail of the efficiency factor, and then let's try to do it and do this problem and preferably let's keep everything in radians. So A was 0.075 per degree, and if I convert that to radian, I'm going to get around 4.3 per radian. And make sure that you convert to radian, because there are a lot of arithmetic that is happening over here which needs your dimensions to be consistent, that to be in radian than in degrees. So 4.3 per radian is equal to 5.72, which we found earlier, divided by 1 plus 5.72. It's nothing but the lift curve slope of your airfoil. Pi aspect ratio is nothing but 1.2 divided by 0.2, which is nothing but 6 times your efficiency factor E. And if you solve this, you can find your efficiency factor is close to around 0.91. And in the question, it's option B. So this is how you find the span efficiency factor. And you can see that it's less than 0.91 because it's less than 1 because it's a rectangular wing and not an elliptical wing. So that is all the aerodynamics questions we have in 2007 paper.